car parking on a hill. The two free body diagrams are basically going to look the same. You've got the car, the force of gravity pulls down on it, normal force is perpendicular to the plane, and then force of friction resists the motion, so stops it from going down the hill. Once it starts sliding, it'll look basically the same. The only difference is your force of friction is going to be smaller. This is force of gravity, force normal. I'll label these two. So when we're dealing with inclines, since nothing is acting in our usual coordinate system of horizontal and vertical, we change the coordinate system so that x is in the direction of travel. So this is our new x, this is our new y, and that means that everything pretty much works out in the new coordinate system except for gravity. Gravity, we will have to break up into force of gravity that's acting in the y, balancing normal, and force of gravity in the x, pulling the car down, that for the first part at least will be balanced by friction. The equations, net force in the x. So I'll start out just by saying that there is force of friction that's negative and force of gravity in the x. In the y, it's normal force plus force of gravity acting in our new y direction. That will be negative. As the car slides down the hill, those two equations are going to be the same, but we're going to put a couple numbers in there in a minute, which is why we are writing this down twice. These two are going to be our negatives. Now, minimum coefficient of friction before the car slides down the hill. To get there, we need friction, and we do need a couple pieces in between. We need to know what force of gravity in the x is, and we need force of gravity in the y. Force of gravity in the x, you should have a note sheet that says something like mass times gravity, which is force of gravity. Sine theta will make it in our new coordinate system. Same thing with the y, but it is cosine theta. So according to me, force of gravity of the x will be about 3,350 newtons. In the y, it will be about 9,210 newtons. So we're going to start to put that into our equations. So before the car rolls down the hill, net force is going to be 0. Force of gravity in the x is 3,350 newtons plus force of friction. So I can pretty much work out that the force of friction is going to be negative 3,350 newtons. And the y is 9,210 newtons. Net force is 0. So I can figure that the normal force is going to be 9,210 newtons. Our coefficient of friction is force of friction divided by normal. So it's basically that math right there, dividing 3,350 by 9,210. And you should get somewhere around 0.364, no units. That's our value for the friction without it sliding down the hill. Now it is sliding down the hill, and the problem says it goes from 0 to 1 meter per second in 10 seconds. So there's your meter per second, and if you do the math, it is 0.1 meter per second is your acceleration. Net force is mass times acceleration. Our mass was 1,000 kilograms. Our acceleration is 0.1, so the math works out to be just 100 newtons for net force. And now our coefficient for kinetic friction. Boom. So sliding down the hill. If our net force is 100, we're still dealing with 3,350 newtons of force from gravity. So now our friction must have gone down to 3,250 negative. Vertically, nothing has changed. It'll be 9,210, 9,210. Boom, this one's negative. But because we have a net force now, friction can be less. And that coefficient of friction will just be, again, coefficient is your force of friction over normal. That means it is 3,250 divided by 9,210. That gives you about 353 for a coefficient. Okay? That's our deal.